In this final video on moments and centers of mass, we're going to deal with the infinite case where we're dealing with centers of mass and moments for a plate. So any shape that you want to consider that might be continuous in nature, something like this, and the points, not only do we have a point here and a point here and all these little points like we did last time, instead we're going to actually have a whole region of points. In fact, a continuous interval of points in both the x and y direction. And each of these points has a weight to it. Of course, to be able to do this using the methods that we know so far, the weight we're going to deal with, we're going to suppose that this plate has constant density. That's just the best way to deal with it for right now. Later on in calculus, we'll be able to do this with variable density, but for right now, let's deal with constant density for a plate. And we want to just find out where its center of mass is. First thing we need to get out of the way is the fact that, well, annoyingly enough, the center of mass for a plate, or a continuous object, is now relabeled as the centroid of the object, the centroid of the object. So I'll usually call it the center of mass, but you may have a text or something like that that calls it the centroid, just to let you know they are the same thing. The only real build-up we're going to use in this video, or the only thing that we're going to change in this video, is, again, talking about a continuous object instead of discrete masses. And like it says in this example, how could we find the center of mass, or in other words the centroid, of a sheet of metal having constant density with upper boundary function f and lower boundary function g, both defined on an interval from a to b? So let me go ahead and draw a possible shape. So the question is, we have this shape here, and it's defined from a to b for both the functions f and the functions g and the function g. Let me draw that in there. And we want to know, where's the center of mass for this object if this object has equivalent density everywhere? It looks to me the center of mass might be somewhere in that region right there, but not 100% sure. In typical calculus fashion, or at least typical calculus 2 fashion, we're going to slice up this interval into little pieces here. We'll consider an interval going from x sub I minus 1 to x sub I. And let's find the average, or in other words, the x value for the centroid. The average weight for the x value, or the x value for the average weight is actually what I'm trying to say. Now recall from the previous video that the x value for the centroid, or the x value for the center of mass, is equal to the moments about the y-axis divided by the sum of all the masses, or the sum of the weight of the object. Now normally the moments about the y-axis would be the summation of the masses times their x values. But because we are doing calculus here, we're going to have a limiting process. And in this limiting process, I have a strange notation here. M sub I is the ith mass, the mass on the interval x sub I to x sub I, or I'm sorry, x sub I minus 1 to x sub I. The x sub I value is going to be, well, the x sub I bar is really going to be just an average point in x sub I. So this is just some average point in the ith slice. Now I'm not too technical with this definition, because the fact is, because we're doing a limiting process, if you go back to this picture, this slice is going to get narrower and narrower. So if x sub I bar happens to be right here for this slice, well, because these green vertical lines are getting closer and closer together, who cares if I say it's in the exact middle or slightly to the right or slightly to the left of the middle? I don't care. It's not that big of a deal. It's just a representative point in that interval. And again, like I said, m sub I is the mass of this chunk, of this little chunk in here. Of course, mass is density times area, so we need to find, they have to obviously give us a density, or maybe not so obviously. So let's go ahead and write that out here. So you see I've replaced all the m sub i's with rho a sub I. In other words, density times area, where a sub I is just the area between f and g on the ith slice, And then A here, this capital A down here, is the total area of the object times its density. So that would be the total mass. Now, of course, we can pull the rows out of this, and the limiting process becomes the summation of just the areas. And we know this from calculus 2 that the area is just going to be the difference between the upper function and the lower function. In other words, f of x sub 1 or x sub I bar minus g of x sub I bar. That will give us the area. Well, actually I have to multiply that by a delta x to get the actual area. So let me multiply the outside by a delta x. So you see in that limit there we have the product of f minus g times delta x, that'll be the area, and then we have x sub I bar. These rows out front will cancel. You know that this limiting process will become an integral, so this will turn into the integral from a to b of x times the quantity f of x minus g of x dx. And that's all divided by the integral from a to b, again because this is the area of f of x minus g of x dx. Now don't go canceling these. You'd be totally wrong if you did that. So don't. Just don't. These are two different values. This is a definite integral up above. That's a value. This definite integral down below. That's a different value. You do not know how they divide into each other, so don't do it. Don't cancel f minus g of x's. This is what it is. And now on to the tricky one. Actually, the first one wasn't so tricky, but y bar, or in other words, the value for the centroid for the y's in the y direction, is going to be the moments about the x-axis divided by the total mass, just like we had before. And along the same lines as we had before, we said that moments about the x-axis is going to be the limiting process, so we sum up the mass times their distance to the x-axis, which is the average, is the y value. Problem is, if we take a look at our plate here, we have a lot of y values. See, it was easy to say the average x value, x sub I bar, is probably right in the middle or something like that. But that's because we were allowing these green lines to squeeze into one another. It didn't really matter what we let the x sub I bar be. But no matter how close these green lines get, the y values can range anywhere between f and g. And that's where the pain starts. So we have to figure out a representative y value, or in other words, an average y value. Well, if you look at this interval, the average will just be the halfway point between this upper y value and this lower y value. And if you do the calculations, the average is just 1/2 of the summation of f of x sub I bar plus g of x sub I bar. So that will be the average y value. So that is going to be what we're going to choose for our y sub I bar. It's just the average y value. And that's where we get this formula. So our limiting process, which was mass times the y value, is now just going to be mass times the average y value, 1/2 of f plus g. And then again down below, I didn't write it before, I forgot to write in the density before, but we also have the density down below here, which is going to get canceled out in a moment when we change out the mass for the area. So just like we did before, remember mass here is just density times the area of the ith slice. So let's go ahead and plug in the area of the ith slice here. So we get this mess down here. Now, let's just take a look what happens. So remember, mass is just density times area. So I pull the density out front. And then the area is just going to be f minus g times delta x. So there's f minus g there, and I just threw the delta x out back. And of course we still had the 1/2 f plus g. So here's the 1/2, and here's the f plus g. Now if you notice this product is actually called the difference of squares. So I could rewrite that as f squared minus g squared. So you see I wrote it to where the density is canceled, so it doesn't really matter what the density is, that cancels out. And there should be a minus sign in here, you can barely see it, but there's a minus sign and all that. And we know this limiting process will therefore become the integral from a to b of, let's see, 1/2 times the quantity of f of x being squared minus g of x being squared, and then dx. And of course, the denominator just is still our area here, which is the integral a to b of f of x minus g of x. And this, again, just like I mentioned in the previous derivation, these do not cancel, so don't do it. That's all I have to say. Just don't cancel these in. The denominator is a finite number. The numerator is a finite number. Whenever you find out what those are, then divide. Don't divide at the beginning. And of course, these results for x bar and y bar are summarized in this theorem. X bar is 1 over a, where, by the way, a in this case they call the integral from a to b of f of x minus g of x dx. So in both cases you're going to divide by this area, but then the average for the x centroid is, or the x value for the centroid is going to be the integral from a to b of x times f minus g, and the divided by the area, and the value for the centroid, for the y value of the centroid, will be the integral from a to b of 1/2 f squared minus g squared, and again that's divided by the area. Those are the derivations, and for the examples we'll wait for class for those.